All right, so my name is Chris McCall. I'm director of the CERN Earth and Space Center here on the campus of Triton College. I would use my video, except for whatever reason, it has decided that my hair is part of the green screen and I come out looking really strange. So I'm going to go back to the still picture just for the sake of not distracting everybody. Anyway, we're pleased to host tonight the Chicago Astronomical Society's monthly meeting. But just a friendly reminder to everybody that there are 2 planetariums in Chicago. We're the one with free parking. Also that we are open to the public. Yes, we're doing summer camps and visiting groups and seniors and college classes, but we are open to the public, at least right now, 4 days a week. With afternoon matinees and programs on Saturday evening. You can get all of that information by going to triton.edu/CERN. And perhaps of special interest to some of the members of CAS and the general public is we're working on plans for celebrating the 50th anniversary of Apollo 17, which will occur in December of 2022, the last crewed mission to the surface of the moon, and hopefully we'll see another crewed mission to the surface of the moon within our lifetimes. But anyway, we're working on plans for Apollo 17's 50th anniversary and have some really cool stuff in the works, including some new interactive exhibits, some new items for permanent and temporary display, and would certainly make it well worth your while to come check us out. So as soon as I have more details and I'm allowed to talk about them, you'll be some of the first people that I'll let know. Anyway, enough yammering about the Space Center. Come visit us. I think I'm going to turn this over to James Kuka, current president of the Chicago Astronomical Society, and I'll let you take it from here, sir.
Thank you, Chris, once again for hosting our meeting. Welcome everybody to the July 2022 general meeting of the Chicago Astronomical Society. Our speaker tonight is Matt Penn, developer of the Dynamic Eclipse broadcast initiative. Matt will describe his citizen science initiative for the 2023 and 2024 solar eclipses, the current status of the initiative, and what we're all looking forward to is how amateur astronomers can join the project. Matt has been doing solar physics research for the past 30 years. Published 70 peer-reviewed journal articles, and has mentored dozens of students. In 2017, he launched a project called the Citizen Kate Experiment, developing the idea of securing funding and working with volunteers. And tonight, Matt is going to discuss the activities of his group and how amateurs like us can participate. So without further ado, I will turn the meeting over to Matt Penn. But I have to mention, Chris, I still can't see a screen. Oh, there you are. Yes, looking good. And there's Mark. Okay. So Mark, Matt, if you can take it away, go for it.
Let me share my screen. And start the slides.
Looks good.
Yep.
All right, it's an honor to speak with you guys tonight. And as Jim has said, the talk will be about the Dynamic Eclipse Broadcast Initiative. This is work that builds on what we did in 2017 for the last total solar eclipse in the country. We've been working for a couple of months now, actually probably just over a year. And right now the team is composed of these 10 suspects. Everyone was part of the 2017, except Castor Fu and Jeff Weiss have joined us as part of the core team for 2024. And this is me, Matt Penn, my Gmail address. So I'll show this at the end as well. If you want to contact me, please do so. And currently my astronomy affiliation is with the Astronomical League. So in way of introduction, thank you for the intro. I just wanted to show you some tourist pictures of the lovely places I've had the honor of working at. I started my career at Big Bear Solar Observatory when I was a student at Caltech. Then moved on to Hawaii to work at the Mies Solar Observatory on Maui. Joined the National Solar Observatory for the first time and worked in New Mexico at the Sac Peak Observatory. Then I joined the faculty at Cal State University Northridge and did some research at their San Fernando Observatory, which is was an interesting location. It was right next to the I-5 and the I-405 intersection. So the LA Basin presented some challenges for observing the sun. And then finally in 2001, I moved to Tucson and worked at Kitt Peak at the McMath Pierce Solar Facility. It was a great move. It was the biggest solar telescope in the world at the time. Actually, it was 3 solar telescopes. So I got tenure with the NSO and started a family. But unfortunately, the NSO decided to close the facility and move to Boulder and notified all the tenured staff that we either had to move or to resign. So in order to keep my family together, I decided to resign. So currently, I am an amateur astronomer. I work as an engineer at Raytheon Technologies here in Tucson. And that means I get to do the astronomy projects that I love and work with the people that I enjoy working with. So nothing but upside, I think. But while I was at Kitt Peak and in Tucson, one of my favorite projects was the Citizen Kate experiment, where we decided to try to observe the 2017 eclipse from everywhere, all across the country, 70 locations. And as part of that, after the preliminary results were in September, we got invited to speak to subcommittees in Congress. And what I'd like to do by way of introducing is to show you a quick little video clip from that testimony. CBS News did a show on one of our groups, and we edited it down to just 1 minute. And I'd like to show you that video here. So here's our Dynamic Eclipse Broadcast Initiative webpage, and you can click on the link here. I'm going to play just a few minutes of this for you.
And finally, my colleague here, Matt Penn, developed an ambitious Eclipse program to combine public engagement with science. And I'd like to share a video about several young people in Dr. Penn's Citizen Kate program.
Gwen and Alexis Cochran are from a Native American reservation school in northern Montana. They took a road trip with their science teacher, Janet Jorgensen, to watch and study the eclipse.
It's just an amazing opportunity for the kids because this is real life science and it helps them be exposed to what kind of opportunities there might be in the future.
These students are one of 68 teams nationwide who participated in an amateur science experiment called Citizen Kate.
We're trying to get pictures of the solar eclipse so we can study the corona.
When the moment finally arrived, darkness descended on the town of JM, and the sight they'd been waiting for revealed itself. A total solar eclipse.
Yeah, it's taking pictures.
Before they knew it, it was over.
Right here. Yeah, we got a few pictures.
Oh my gosh, it's so pretty.
But for these kids from a remote Native American reservation, 2 minutes and 27 seconds will stay with them for a lifetime.
It was just something you don't forget, I guess. Just
This eclipse changed their lives.
Kayla, get back to the slides.
Nice. That was very nice.
They did an excellent job on the CBS side, and if I can get back to this. I think that little clip really encapsulates the three things that we were trying to do with Citizen Kate. One was to, provide an opportunity for kids who didn't really necessarily have those. In that case, this group from a Native American high school, and then do real science, do real citizen science with our data. And I'll show you what we did with that as well. And then have outreach. So the fact that it was on CBS this morning and showed, the solar corona, I think is a win. Anytime you get to see the sun on the TV, I think is a big bonus. So what was the science we were trying to do? I'll divide this talk into thirds. This is the intro about the general science from eclipses. Then I'll talk about Kate in detail, the mechanics of what we did. And then finally, talk about the DEB initiative and what we're doing now and how you might join in. So as you all know, our colleagues at NASA study the sun from space all the time, every day. So what can we do from the ground, especially with small telescopes during an eclipse? Well, NASA studies the solar corona, which is the hot atmosphere of the sun. It has temperatures between 1 million and up to 25 million Kelvin, with a variety of spacecraft. The NASA SDO spacecraft has an instrument called AIA, and that takes really beautiful pictures of the disk of the sun. The corona is seen right up against the disk, but these are limited. They're limited to particular temperature bands. So if you think of H alpha, you only see one temperature gas in H alpha in your solar filter. The same thing happens with the NASA SDO images. You only see particular temperatures of the solar corona. However, NASA uses the LASCO C2 instrument to look at all of the plasma in the outer corona. This uses white light, just exactly what you see during an eclipse with your eye. And it measures electrons. So every electron in the solar corona, in theory, is measured with white light. The problem with the LASCO field of view is that it doesn't go below about 2.5 or 3 solar radii because of scattered light issues or spacecraft jitter, pointing jitter. The field of view is cut off. And so what we can do during an eclipse is study this inner region of the corona that is not studied at all temperatures with NASA SDO images and is below the field of view cutoff for the LASCO white light coronagraph. So here we have our Kate image from 2016 superposed with simultaneous data from the 2 NASA spacecraft. And you can see we almost fill in the entire gap. We missed a little bit, but for 2024, we're aiming to fill in the entire region. So we can actually be really useful in terms of space observations. What about from the ground? I mean, a lot of the telescopes I showed you, we also used to study the corona from the ground. But observing the corona from the ground out of an eclipse is limited by scattering from the Earth's atmosphere. Now, this is an example, and hopefully your room isn't as dusty as the room on the left here. But if you held your thumb up and blocked out a bright light in your living room, you would see dust and other particles in the air scattering that light around your thumb and entering your eyeball. The same thing happens in the Earth's atmosphere, where light from the solar disk, and that's 1 million times brighter than the corona, is scattered off of dust or in the Earth's atmosphere, nitrogen molecules, and enters the telescope. And this really inhibits our ability to study the corona from ground-based telescopes. The sky during an eclipse is about 10,000 times darker than the sky at the best solar observatories. And that's, of course, because the moon is blocking out it's casting a big shadow on the atmosphere of the Earth. And so that reduces the scattered light background enormously. So we can do really well compared to space and other ground-based telescopes, but what type of science do we want to study in this region of the corona? It's important because it's basically a region where the plasma is accelerated. It's like the on-ramp, the freeway on-ramp to the solar wind. when NASA looks at velocities in the solar wind or outflows and coronal mass ejections with the LASCO C2 instrument, all they see is a constant velocity. These things are moving at 200 kilometers per second or sometimes up to 800 kilometers per second, but with constant speed. We know that they start at zero velocity on the disk of the sun. So somehow between the surface of the sun and this region at 3 solar radii, they have to accelerate from 0 to 200 kilometers per second, just like you do on a freeway on-ramp. And so that was the main focus of the Citizen Kate experiment, was to try to observe plasma in this region and watch it accelerate. And I hate to use an equation, but in physics, you all know that force equals mass times acceleration. So one of the key questions in the solar physics today is what kind of forces are accelerating these particles into the solar wind? And by measuring the acceleration profile, we can help distinguish between different models that rely on different forces, for instance, on waves or on magnetic fields. So that was our goal. And during a solar eclipse, which lasts only about 2 minutes or maybe 4 minutes at one location, you don't have enough time to really track a particle very far through the corona. So that's why we established a network in 2017. We had 70 locations from Oregon to South Carolina. And instead of just being limited to a few minutes of time, we could observe flows for 90 minutes of time from the time that our sequence starts in Oregon until it ends in South Carolina. Now, this is a map of the day of the eclipse. And so unfortunately, we had some spots with clouds and a few gaps in our data. But still, this was an unprecedented time sequence in terms of images of the inner corona in white light. Nobody had done this before. Here's a sample frame from our movie sequence. And I won't try to show you the movie, but I'll point you to this webpage at SIU Carbondale. Here you can find links to our papers as well as a link to the movie. But in our sequence, we see a lot of interesting things. We see acceleration at the north and south poles of the sun. We see interactions of the chromosphere, the material that you look at with your H-alpha solar filter. We see that interacting with the corona, the hotter plasma. We see some stars, some background stars in our sequence. But the main thing that we see is an outflow, which is following a coronal mass ejection. This CME happened about 1 hour before the total eclipse, but we still see plasma rising off of the sun through the corona during our eclipse sequence. And that's really what we focused on as the most dominant thing that you'll see when you check out our movie. And so it took a little bit of time because, like I said, I'm an amateur astronomer now. But about 2 years after the eclipse, we had aligned all the images and measured the motion of these particles or these blobs of plasma in the corona. Here you kind of see a blow up of that area and superpose our vectors of motion that are detected in our sequence. But here you see a graph of that radial motion. So the radial outflow speed varies from 0 up to 350 on this scale. And horizontally, we go from the surface of the sun at 1.0 up to 4.0. So LASCO is shown with this solid line. They measure this event flowing from the sun at about 250 kilometers per second. And then the Kate measurements are the dots that you see here. So you can tell we're doing real science because it's complicated. It doesn't fit, our observations don't fit any easy models. If the material was accelerated with a constant acceleration at 15 meters per second squared, it would follow this dotted line. If it was accelerated with some sort of ad hoc 175 kilometers per second per radius, it would follow the dashed line. And you can see it doesn't follow either of those lines. There's something complicated happening. But this is the first measurement in white light showing all of the gas in the solar corona of the acceleration profile. And it matches fairly well with the LASCO, asymptotically at 250 kilometers per second. So that's the science that our Citizen Kate experiment concluded with. If you type this into your Google search engine, you could take a look at our paper. It's got a lot of details that you may not be interested in, but it's open access so that everybody can read it. Co-author with 286 people on this paper. So all of our site volunteers were co-authors with me. So that's kind of the introduction to eclipse science. Any questions about that? All right.
You said, you said that the particles accelerate from 0 to what speed?
Well, in this case, they're accelerating, or they're traveling at 250 kilometers per second when the NASA LASCO mission sees them. And they maintain that speed roughly through the whole solar system. There's some blips, sometimes they slow down or speed up. But this is a rather slow ejection off of the sun. Some of the coronal mass ejections can travel at 800 kilometers per second, just ridiculous speeds.
Matt, just out of curiosity, what is the escape velocity from the surface of the sun?
Oh, that's a good question. It's small. I think tens of kilometers per second. I think down.
I see. Okay.
Down around 50. I'd have to look that up. I'm sorry.
No, it's all right. I can.
Good question. Good question. Any other questions about the intro science?
Nothing in the chat.
Excellent. Okay, so I'll spend a couple of minutes now talking about how do we do this? How do we get this huge project together and get a science paper out of it? Well, this is a really schematic outline, but we did a couple of practice runs, and there are roughly 1,000 days before the 17 eclipse and roughly 500 days before the 17 eclipse. And I'll talk about these two and then more details about what we did between, for the last 500 days leading up to 17. So for the first event, it was an eclipse in the North Atlantic off of the Faroe Islands. Volunteer Fred Isbener from Carbondale, faculty, retired faculty there, said that he was going there on his vacation with his wife and his friends. And so I asked him, well, can we ship you a telescope and train you about how to use it? And would you collect data for us? And he said, I've never taken a picture through a telescope before. So we worked with Fred. It was in the winter in Carbondale. So you can imagine that it was a little tough to get some clear skies, but he picked up a telescope in the Faroe Islands that we had shipped, set it up basically in the rain and clouds on the morning of the eclipse, but nonetheless captured some images during totality. So these are actually Fred's very first astrophotographs. And, I have to admit, we gave him crummy software and we switched cameras. This camera turned out to be pretty poor. But this was a real proof of concept. Here we took an excited volunteer who hadn't done any astrophotography before, and he met all the deadlines and came away with data, images from the Faroe eclipse. So we learned a lot, and I'm forever indebted to Fred as acting as a guinea pig for us. And in 2016, we decided to basically train some people by sending them to Indonesia. So we partnered with 4 universities: Carbondale, University of Wyoming, Western Kentucky, and South Carolina State. All 4 of these were in the path of the 2017 eclipse. So from each institution, we had a faculty mentor and a student travel to Indonesia. We set up 4 different observing locations, hoping to test out the idea of a network. And we came back with a better image. We had better equipment, better software, better hardware. But unfortunately, the weather was only decent at one site, and we had high clouds even at this site. So we didn't collect as much data as we were hoping to. But the important thing was that we came back after Indonesia. Now we have 4 undergraduate students who are experts. They have on-the-job training during an eclipse, and for faculty mentors who also had on-the-job training. So they know all of the details about what can go wrong and how to make sure that you get data during the eclipse. So we leveraged this and had each of those 4 people act as state coordinators for their states or neighboring states in some cases. And then to that, we added 5 more volunteers to act as state coordinators. So leading into the 17 eclipse, we had a preliminary list of sites where we would have volunteers observing the eclipse. But I have to be honest, I don't know anything about observing in Oregon where the good locations are. We just use Google Maps. So, but Mike Connolly knows a lot. He's a very active amateur astronomer in Oregon. And so we used his knowledge, his local knowledge of the Oregon weather and sites to refine the locations of our sites and to select volunteers to coordinate with them. Here's Mike in Salem on the day of the eclipse getting some excellent data. At the beginning, you can see the telescope is really low as the sun is near the horizon. But our state coordinators really did a fantastic job. They were in charge of defining the observing sites, sort of finalizing the observing sites, and then working with the site volunteers during their training and subsequent testing. So here are our site volunteers. We had a huge group of universities, 27 universities represented and 22 high schools along the path of totality, 8 informal science education museums, and then 4 national labs as well participated in the project. And these were the people who were doing the real work. They volunteered to travel to a particular site. They used the equipment, met the deadlines. In some cases, we had a lot of public interest. And so they had a person sort of handling the outreach and keeping them away from the equipment during totality. But these groups did all the work. So the first step was to give them the equipment. And we were lucky in that we were able to raise funding to buy equipment for all of our site volunteers. We had training workshops in each state where the volunteers would travel, and that's where we gave them the equipment, and then they owned it after that. So we trained them for a day or 2, depending on the location. And they took the telescopes home and started practicing with them. You can see that we had snow in our Wyoming training. And then in Tucson, it was 105 degrees in the shade. So this also served as kind of an environmental check on our equipment for the eclipse. So after the training workshops, which ended around, I think May, we were able to hire those 4 undergraduate students and a couple more in Tucson for the summer. And they worked with the state coordinators and the site volunteers during our observing campaigns. We had 4 or 5 days where we asked the site volunteers to just take the telescope out in their backyard and take a picture of the sun to practice on. The data would come to Tucson. The students would take a look at focus, at alignment and exposure, and then provide feedback back to the site volunteers. And we iterated back and forth 4 or 5 times. And we saw a definite improvement in things like focus and alignment. So then on the day of the eclipse, the weather, pointed out the cloudy spots, but the weather is fantastic. We have scientific data from about 50 of our 70 locations, which is outstanding. I never have that luck when I did observing runs. Again, about 260 volunteers, 117 students. And the sites here span the gamut, right? So this was kind of a lonely hilltop in Oregon. Again, sort of a field in the middle of nowhere in Nebraska, kind of a suburban location in South Carolina, and then, a huge stadium in Carbondale. So, personally, I'd rather be in the field taking data than having 50,000 people screaming at me trying to take data during the eclipse. But there's a variety of experiences that our site volunteers had. I was really happy to work with the local high school, Seneca High School, who shipped out to Pawnee City, Nebraska, which basically was in the middle of one of those cloud belts. They were rained on as they prepared for the eclipse. But we had some standout students, Savannah and Ella. I think, excuse me, one of my favorite shots is them like holding a poncho over the telescope and another one over the computer. I'm thinking, oh, that doesn't look too safe. But they stuck with it and took data and got some interesting structures during a period where we had a big gap, but would have otherwise had a really big gap in our movie sequence. Many of these students since gone on to undergraduate programs. I know Savannah's majoring in math. So the education and the science, the data collection went well. In terms of outreach, I personally went to Weiser, Idaho, a town of like about 2,000 and 20,000 people descended on the town. So there are festivals all over the place. A lot of our CATE sites, and especially in smaller locations, acted as a nucleating site. And like I said, some of the CATE volunteer groups had to have people in charge of outreach. And we had a big impact, a big footprint in print, radio, and TV. Now, after the eclipse was over, we were hoping to do a lot of follow-up science. And we've done some, but this was one of our weaknesses, I think, one of our weak spots. We did some lunar occultation observations with the telescope. In Tucson, Savannah again, and several of her colleagues won, state science fair prizes and nice scholarships with the work that they did. Zach Stockbridge got together a group of CATE volunteers and observed the transit of Mercury from different locations across the country. And then we actually took some observations of an exoplanet. So Mike Connolly in Oregon, again, used his CATE equipment, and his data is published in a paper by Robert Zellum in 2020. So we were able to make some headway, and some people are still using their CATE telescopes for outreach events even today. But we're hoping to improve upon this as we move forward. Okay, and then finally, here's the funding, right? So how do we actually pay for all of this? The equipment for every location was about $3.5K. So our total budget was about $260K. And we had very generous corporate donations. Daystar Filters gave us 60 telescopes. Celestron gave us 60 of their equatorial mounts. MathWorks provided software. A color maker, this is a food dye manufacturer in LA, just gave us $10,000 cash because the CEO is an avid amateur astronomer. And then for our hardware, the National Science Foundation provided us with a nice grant to round out the pie here. NASA provided this big education chunk, which enabled us to practice in Indonesia and hire the students during the summer. Okay, so that's the 17, the mechanics behind the 17 event. Any questions about that?
None here, sir.
Okay. So
Speak up, everybody, or unmute yourselves.
What are we doing now is the next and the final part of my talk. And it starts with what do we want to improve, right? So I remember telling several newspapers and I think a TV reporter in 17 that I wanted to make a movie of our data and show it that night. And that was a major underestimation on my part. I said that no one had collected data like this before. And the corollary to that is that no one has ever analyzed data like this before. So as you can see, it took several years to figure out how to align these images to make a decent movie. We'd like to fix that this time around. So that's why we're calling it the Dynamic Eclipse Broadcast Initiative. We really like to have a real-time web presence during the day of the eclipse and show the evolution of the corona in real time. So this is a big goal that we're aiming for right now. We like cheaper equipment. And for a while, we were using these wonderful Raspberry Pi cameras and Raspberry Pi computers. And it turns out the rest of the planet has also decided to do that too. So if you try to find a Raspberry Pi computer to buy now, you're either going to pay 3 times the original cost or you can't find it. It's basically impossible to imagine getting 30 or 50 of these now. So we're steering away from Raspberry Pi. We're going back to a more standard Windows and standard camera system. But again, we still want to keep it less expensive than we had in 17. In 17, we only had observations from the path of totality. We'd like to change that and have observations from the partial phases as well. And then, like I said before, we'd like to make it easier to do follow-up nighttime work. Part of that is using a go-to mount. The other part is now we're practicing on lunar eclipses. So we're already doing nighttime work from the very start. So then, the timeline looks a little bit more complicated than the 17 timeline. I'll talk about the lunar eclipses and the total solar eclipse that we sent equipment to. These are in green, and that's basically about 1,000 days before the eclipse. Coming up in October is a partial eclipse from Europe. It's about 500 days along with a lunar eclipse here in the US. And then we have a rundown to the totality day, t equals 0. The annular eclipse in 2023 is something that we'd also like to observe, but it's only 6 months before the total eclipse. So we can't really make any adjustments in here. It's really too short. And there's hope that we can get funding to actually send some students to Australia for a total solar eclipse in 2023 with a equipment package. So looking at some lunar eclipses, we established a network for the November 2021 eclipse. Out of the 8 sites, we basically had 2 that were clear: Greenville, Texas, and Tehachapi, California, with Claude Plymate here and Bill Klepping in Texas. So each of these fellows were using a Raspberry Pi camera. And let me show you some of their data. So here's a picture from Claude's sequence. He was feeding it with a 135 millimeter lens, just a Nikon lens. The eclipse was not exactly total. It wasn't a total lunar eclipse. I think it was 98, 97%. So you'll see a bright ring where the part of the moon is still in the penumbral shadow, much brighter. But you can see background stars and some of the clouds that Claude was fighting. Then from Texas, Bill Klepping was using a 105 millimeter Nikon lens to feed his Raspberry Pi camera. You see the same background stars, the same bright section of the moon in the penumbral shadow. But we've aligned these two, and these images were taken about a second apart from these 2 locations. So from the 1,200 mile baseline between Tehachapi and Greenville, you get a parallax. So you're able to see the moon in different locations against the background stars. So the obvious thing to do is to make a 3D image using Claude and Bill's lunar eclipse images. With a 1,200 mile baseline, the shift is pretty big, and this is on our website. So at your own leisure, please take a look at it with your 3D glasses. I have a hard time with my old eyes getting these to merge, but a lot of younger guys can do it easier than I can. What we're hoping for the future is to get a shorter baseline. Something like 500 miles, I think, would make an excellent 3D image, easier for people to see. But in November, this is our goal, as well as to upload images in real time. And we achieve those 2 goals with the Pi camera. As sort of a short notice event, Fred Isbner again said that he was going to a solar eclipse, this time in Antarctica, with his friend Alan and his family, their wives. So with about 2 weeks to spare, we were able to ship Fred a Pi camera and a 50 millimeter lens. 7 years makes a big difference. This time it fits in a Tupperware container instead of suitcases. The weather was really bad. As you probably heard, there were 6 cruise ships in the ocean, and only one, luckily it was Fred's ship, actually saw any of the eclipse. So here's the only image he came away with. He was frantically moving from one side of the boat to the other and missed totality. But here's the ocean, and then here's the cloud deck. So
Oh,
the
wow.
captain of the boat managed to get, like a 1.5 degree window where they did see visually, they saw totality. But in terms of images, he was only able to capture the partial eclipse.
Nice.
So our next event is in 2023. Hopefully we'll have, again, funding to go there and better equipment as well.
I'm just going to interrupt here. Somebody typed us a note in the chat, said, very impressive effort and admire the enthusiasm and student engagement. Thank you for doing it.
Well, I can honestly say it's my pleasure because I'm an amateur now. I'm doing it on my free time. So yeah, it's just a joy to see students and their reactions, right? And hopefully we're inspiring them to, if not go into science, at least think in a scientific way for the remainder of their lives. So this is our attempt at the solar eclipse, and we're hoping to do another one. But in the meantime, we were able to get a good view of the May lunar eclipse. In this case, I think we had data from 4 sites. I won't show you the movie, but again, please take a look at YouTube, and it's also linked to our Deb Initiative webpage. An enormous number of background stars in this case. And as the movie sequence goes back and forth on the YouTube page, you'll see the moon occulting and revealing a lot of these stars. Our hope is to do a 3D movie, but that'll take some time with the data. But I don't think anyone's done a 3D movie of a lunar eclipse ever.
Yeah.
Might be interesting.
Matt, what is it about the Raspberry Pi camera that makes it good for eclipse imaging?
Well, there are 2 things. One is that it's a decent size. It's a 3K by 4K array. The best thing is that it's $50.
I see. Okay.
But
That helps.
Like I said, it has drawbacks. It's color, so RGB. I've never really done science with a bare filter with a color camera before.
Yeah.
But the major drawback now is that you can't really get a Pi computer, a single board computer, to control it.
I see.
The supply is gone. There's a website called rpilocator.com, which has a web crawler looking at all of the international sales sites. On any given day, there's either no Pis for sale or maybe 2 sites have a couple of Pis. So it was a fun adventure to go through that for a couple of months, but it didn't lead to a viable equipment package. But so when I did visit, Chicago, and I've been traveling around carrying a telescope and a camera, much to my wife's dismay, but we traveled to Chicago in March. And then I was also using the Pi at that point with a 30 millimeter feed telescope. Here's the image that I got from outside, from the parking lot of Adler. Decent seeing. We could see some small sunspots and then some plage around the limb. But again, we're moving away from the Pi. Again, it fits in a Tupperware bin, and this is what I like to carry to the partial eclipse, which is happening in October. So since March, I've been refining it down and taking it along on our family vacations for wine tasting in Paso Robles and family visits in Missouri, and then on my front deck again. Basically, I think we've settled on the 30 millimeter feed telescope, but for the upcoming project, I think we're going to try to get a bigger aperture, a 40 or 50 millimeter telescope. That's the last component that we're still looking at. I think the ASI 178 mono camera is doing a great job, and I think we'll stick with that. And for this portable setup, I'm just using one of these Star Adventure minis, but we do have 2 go-to mounts that we're looking at recommending. But from my porch with the 30 millimeter front end, this is the type of resolution that we're able to get. And this is what I'm hoping to transmit from Greece. So the idea from Greece is to take the data. We're using SharpCap to collect the frames, do a quick reduction on about a minute's worth of data. So for that, we're using a Python script that's pretty close to AutoStacker. It's called a PSS. And then the last step, we're still farting around with this, actually taking the images. We're able to move it to the cloud pretty obviously, or pretty easily with a Wi-Fi link on my cell phone, for instance. But then displaying it on a web page is the last step that we're still working on. So we'll get that step figured out for October, and hopefully on the 25th, you'll be able to log on to our webpage and watch the partial eclipse in real time.
Matt, one of the challenges that we had in 2017 was achieving a good focus.
Mhm.
Does your group, your website offer, any suggestions, ideas of how to achieve good focus for an eclipse photograph?
Well, the best way is, of course, with spots. And here, from this was a few weeks ago, we got plenty of spots now, and hopefully we'll also have spots for 23 and 24.
I got
But
you.
for 17, what we did is we developed a script that looked at the gradient at the limb. And so we would take images at real time, I don't know, 10 frames a second, and just measure the gradient across the limb and print out a number. And the site observer would dial the focus and try to maximize that number. And when he did, then that was the best focus. And I have to say, we had excellent results. I mean, a lot of people say for eclipses, half of your telescopes are out of focus, but again, we had about 50 telescopes with science quality data out of 70 sites. So we can talk about that, and certainly if you're interested, we can provide the pseudo code or maybe even Python code to do that.
Yeah, that would be great. We couldn't find any, background stars to focus on. But certainly if, there are sunspots, well, that would, provide us with something to focus on. So
If you're okay, changing the setup during the partial phase, the limb of the moon is also an excellent place to focus as it moves across the disk. But I mean, some people want to get set up well before, as we did.
Timing is a big challenge. So thank you. That's very helpful.
So for the 23 and 24 eclipses, our equipment is kind of narrowing down into this sort of setup where we're probably going to use the ASI 178 camera. Again, it's a large camera, or larger than other cameras in its price range. I really like the optics in the ASCAR refractors, but we're also testing a William Optics 50mm uniguide. But basically what we're, as you can tell, building here is a really good guide telescope, right? Maybe some of your advanced astro imagers have this set up already as something that they guide their imaging telescope with. And we're doing this to get the field of view that we need without sacrificing too much in terms of spatial resolution during the eclipse. So there's kind of a tiered system. If you already had a mount and a laptop that you're comfortable using, then this setup costs about $800. If you want to buy a mount and a cheap laptop, it might be more like $1,500 or $1,600, but we're still well under the $3,500 price range that we had in 17. So we're hoping to be able to get a few smaller proposals funded and still be able to provide equipment for our site volunteers. So moving on to the events in particular. So in 2023, what we have is an annular solar eclipse. So it has a central path, just like a total solar eclipse does. But in this case, the moon is slightly further away in its orbit from the Earth, and so it appears to be slightly smaller than the disk of the sun. And during totality of an annular eclipse, you don't see the corona. You just see a bright ring. It's called a ring of fire in some cases, a bright ring of solar photosphere coming around the edges of the moon. And then, of course, outside of that path, you just see a partial eclipse as the moon doesn't intersect with the center of the solar disk. So for the annular eclipse, we're hoping to set up a network of sites. I'll probably be someplace in eastern New Mexico looking at this. And what we're trying to do is to do something that I've never really thought of and was really presented in a very visually stunning way by Wang Li Qian, who put this together from an annular eclipse in China in 2020. So the central frame here is during the center phase of the annular eclipse. Then he stacked a sequence of exposures. I think they're about 2 seconds apart, preceding and then following the annular eclipse. And what you get here is sort of an inverse profile of the lunar limb, right? The dark areas are where mountains on the moon are blocking the sun,
That's
and the
cool.
light areas are where the valleys of the moon are letting the sunlight in. So this is a great image, but what advantage does a network give us? So if you've ever made a movie of the moon through a couple hours from your backyard, you'll see something called daily libration. And what's happening is that obviously your telescope on Earth is being swung through a couple of thousand miles as the Earth rotates. So during just a 4-hour period, you're getting a nice parallax angle, and you're seeing the different parts of the moon throughout the night.
Wow.
So as the path moves from Oregon to Texas, we're going to have different parallax angles looking at different parts of the lunar limb. And so my hope is to make a movie sequence of images like this. I call this a Bailey beatogram. Maybe I should call it a different thing to honor the original photographer. But it would allow us to see different parts of the limb of the moon as we get different views based on the parallax from our different observing locations. So that's kind of the incentive for being along the path, the center path for the annular eclipse in 2023. And right now we only have a couple of volunteers, and it's maybe a lower priority than 2024. But for those people who observe in 2023 and also people outside of the path of annularity, we'd like to start taking regular solar observations, similar to the one that I showed from my front porch there. Because as the sunspot cycle activity starts to ramp up, we're going to have things called white light flares occur. White light flare is visible, obviously, in white light, and represents sort of the strongest X-class flares seen in solar activity. We have some images from, in this case, the infrared that we took at Kitt Peak, but they're also, the flares are visible. The bigger flares are visible in visible light, 500 nanometers wavelength. And some of them are very exciting. In one case, we actually saw a white light prominence lifting off of the limb of the sun. It was just in a projected image at the McMath Piers, and it freaked all of us out. We, had combined like 150 years of solar observing experience, and none of us had ever seen anything like this. So having a network of telescopes that were regularly observing the sun, especially during the peak of the next sunspot cycle, would provide some stunning images of white light flares. So that's another sort of longer term idea for people involved in the project. But then finally, 2024 is the culmination of the DEB initiative. Here's the path of totality. It starts off the coast of Mexico, goes through Texas, up through the center of the United States, skirts the northern edge of New England, and then out through Nova Scotia and Prince Edward Island, Canada. We have sort of a preliminary site list for about 40 sites along this path that would give us continuous coverage. But we're refining that and looking for local experts to basically tell me where I'm wrong and where a better location would be. And we're looking for site volunteers. There's about 3 or 4 people again who have volunteered at particular locations to take data. And again, our goal is to have something like this. There's a sketch of what we hope we'll have on the day of the eclipse. So even if you don't participate by taking data, hopefully from your computer terminal, you'll be able to log on to our webpage, see live images during the eclipse, and click on each one and see a movie sequence from that site.
Yeah.
So last slide is how can you get involved? Well, again, we've got a core team, only about a dozen of us now working on hardware and software. If that's only part of what we could do, we could also work on curriculum and public outreach. So even if your immediate goals don't fall into hardware and software, we would like other people to volunteer for other aspects of the project. The next step is to get state coordinators who agree to help manage a region of the country, basically interfacing with the core team and with the real people, the site observers. Hopefully we'll be able to provide funding for their tests, for their hardware, but we may ask some people to actually purchase that and to take observations. Or, in several cases in 2017, we had a scientist who, worked with the local high school, and he led them and let them kind of experience the data collection on their own, but acted as an expert. So if you have a favorite high school or school group that you want to work with, and you want to act as a sort of a subject matter expert, then that would be great. Please contact me either here at Gmail, or we have our group email. Then our website is here, and I think it's in the email announcement as well. So that's all I had. I'd be happy to answer any questions.
Your YouTube says it's not up there anymore. It was taken down. The video isn't available anymore.
Oh, I'm sorry. At the SIU webpage? Oh, or at the YouTube webpage?
Well, the YouTube webpage, and I can't find anything on the SIU webpage. It just goes to their main page, and it just says SIU Department of Physics, and don't know where to go from there.
Okay. If you would send me an email, I could send you direct pointers. They flash by pretty quickly, or I may have copied the wrong address. I apologize. But if you could just send me a note, then I'll point you to the right spots.
Hey, Matt, I guess I'll send you an email as well. This is Chris. I'll send you an email as well. And if you can confirm the web addresses, we'll add them to the notes under the when the talk gets posted to YouTube.
Excellent. Thank you. Yeah, I'm sorry. It was
Nope.
cut and paste problem.
Stuff happens, so it's okay. Anybody else have any questions, comments? Where are you gonna be? Where are you gonna be in? Oh, hang on here. From a random Samsung phone, I believe here is, thank you, Matt. Fantastic presentation. We'll contact you via email about volunteering. Cheers. Giovanni, thank you all.
Excellent.
Yeah, I second that, Matt. Here in Chicago, observing, the night sky is, next to, well, severely limited, but the one thing we can do is observe the sun. And we are looking forward to, the upcoming events, and don't be surprised if we, ask you some questions in the coming months and years.
Excellent.
And again, we thank you so much for the time and effort to educate us. And as Chris mentioned, this your talk will be is recorded and posted on what, YouTube, Chris?
Yes, sir.
Yeah.
YouTube for the CERN and Earth and Space Center.
Right. So
Thank you, Chris.
This was very helpful, and can't thank you enough, Matt.
My pleasure. And
It
I'm
is-
looking forward to any questions or follow-up comments you guys have.
So a couple of quickies from me. It is mattpenn@gmail.com. 2 T's, 2 N's.
I'm sorry, it's yeah,
Matt-
two T's, 2 N's, Matt Penn 2015.
Oh, 2015. All right, that's what I needed to know. I knew there was an appendix to it.
Yes. at
Okay.
gmail.com.
I didn't know if you were going to talk about weather or not. I think the general consensus is the weather here in the Midwest probably won't cooperate. Some of us did not get to go to 2017. So where is it that oh yeah, that's right. You said you were going to be in New Mexico.
Yeah, for the 23, I'm going to be in New Mexico. The weather, I think, for both events is better in the southern parts. So for 24, the best weather is in Mexico and South Texas. I'm thinking in 24, I'll go to a place called Uvalde, Texas, and work with the schools there.
Oh, wow.
But I'm giving them a little bit of time to recover from the
Yeah.
trauma that they
Are
received.
how close are they on the center line or fairly close?
Fairly close enough.
Oh,
So,
wow.
yeah, I think that's an obvious place to go and do some good stuff.
That would be tremendous. Absolutely tremendous.
Well, I suspect we will have a number of CAS members trekking down to Southern Illinois, which appears to be in the path of totality. So,
Oh, yes. Yeah,
yeah.
Bob Bear at Carbondale, and I think NASA Edge will also be there for the 24 eclipse. So they will have an enormous event again for 2024, and hopefully good weather, but April is tough, as you know.
Exactly. We feel that we were very fortunate in 2024. And so anyway, again, thank you so much. I'm going to leave the meeting and let you close it down, Chris.
Okay.
If there are any more questions for Matt, fire away. And, I will be following up with you, Matt, and, thanks once again.
Thank you, Matt. Appreciate it.
My pleasure. I'll talk to you guys soon.
Okay. All right, everybody, have a good, safe night. Looks like a clear sky. As clear as it gets in Chicago. All right. I'm gonna turn off the recording. Good night, everybody.